So, hello everyone, welcome back to the third lecture for PCA, and this is going to be the last lecture for PCA. So let's come to the agenda for today. Okay. So the agenda for today is this, that we will talk about more, we'll talk more about the SVD version of the PCA. Then we'll see another version of the PCA, which is via the reconstruction error. Then we'll look at some of the applications of PCA, and one of the applications is feature importance. So we'll slightly look at that from a little bit of more detail. And in the end, we'll solve some questions as well. So let's start. So I had given you this DPP yesterday. Have you guys solved this? Can you let me know the solution? What solution did you get?
Just give me 2 minutes. I'm looking for the copy actually. Yes,
Okay, fine. Vashita, solution? Tell me the eigenvector that you found. Or the eigenvalue corresponding to which you have taken the eigenvector. Okay. So I have attached the answer here. So you guys can check your answer. So I'm not going to solve this because it's simple diagonalization. You just have to find the eigenvectors. So first of all, you will zero center this particular matrix, right? Once you have zero centered this matrix, you will calculate X transpose X, which is a 2x2 matrix. Then in this particular question, you might choose to divide by 4, which is like m is equals to 4, or not, because eigenvectors really don't change if we multiply them with something. So there are 2 eigenvectors that we'll get. So one eigenvector is corresponding to the eigenvalue 16, and this is corresponding to the eigenvalue 4, and we will choose this one. Also, negative signs are also okay if you have negative signs with this, right? So this is the solution for your PCA. That's simple. Okay. Rohan, fine. Okay. Now let me proceed with a question that was asked yesterday. That in the SVD version, I did not explicitly showed you that where is the variance and covariance coming from. So I will give you a very small proof. I'll show you that the matrix, this V is same. Either you go via the variance, the EVD way or the SVD way. Okay. So this is the SVD that we had seen in the linear algebra. This is M cross N matrix, right? And this is M cross M matrix. This is M cross N diagonal matrix, and this is N cross N matrix, right? So what I will do is I will prove that if I take this version, right, and I compute X transpose X, and I do the diagonalization of this, then this matrix V, right, will be the same matrix that we'll get. Fine. So let me start with the proof. It's a very simple proof, nothing very fancy about it. So what we'll assume is that this X is a M cross N matrix. It's not a square matrix. And also that we are using SVD version. Okay. So how will we calculate X transpose X? So X transpose X, if I have to write in this form, will be this. So I'll just replace X with Q, sigma, and V transpose, and X transpose with the transpose of this whole thing, right? And I can then do some reductions. What is this? Okay, so this is I. What is the dimension of this matrix? So this is M cross M. This is M cross N, and this is N cross N, right? So this is a M cross N diagonal matrix. Sorry, it's a M cross N M matrix. This is also M cross N. This is also M cross N. Why is this identity? U transpose U is equals to identity because they are orthogonal matrices, right? Orthogonal matrices. Since orthogonal matrix. U is a orthogonal matrix, hence we can write it to be I, right? Now see, this is sigma, so I will write it like this. I sigma, this is transpose and B transpose, right? Now, what is the dimension of this? Sigma transpose, this is N cross M, this is M cross M, and this is M cross N, correct? I can do further reduction. I can just get away with this, right? I can multiply this with this. No, I was writing for this. This is this. Sorry. This is for this. This is this. And this is for this dimension. I'm looking only at this piece of matrices. Okay. So I can multiply identity with this. Right? This is M cross N and this is M cross N. So I can get away with this matrix. So what will I be left with? I will be left with this. Correct? Yes? Fine. So let me come to a cleaner version of this. Then this matrix, I can just write the square of it, right? So this is a M cross N matrix, and this transpose will be N cross M, right? Yes, this is N, right? So what is happening is that your singular values are just getting squared, right? And see, I started with this definition of X that I will take the SVD. Even when I am taking X transpose X and I'm doing diagonalization, this V matrix is same, which is coming from the SVD, right? Hence, even if you do SVD and not EVD, your diagonalization matrix or the matrix that diagonalizes the right singular vectors are actually your eigenvectors of X transpose X. Make sense? And hence I can do the SVD and get away with it rather than computing a covariance matrix and then doing an EVD. Fine. So these are actually equal forms. Okay. So just the conclusion that the EVD of X transpose X shows that the right singular vectors, this is actually P of X, are equivalent to the eigenvectors of X transpose X. Fine. And singular values sigma are equal to the square root of eigenvalues lambda of X transpose X. Fine. Clear? Now we are clear that why can we do SVD rather than just doing EVD? Fine. Okay. Now let me go to the third version of PCA, which is the reconstruction error. Okay. So let me give you some context over here. So this is a image from MNIST. I have already told you many times that MNIST has is a data set which has handwritten digits. Okay. So this is a 5. This is the original image that I've taken from MNIST. Okay. Now, what have I done here? I have actually taken the projection of this particular image, and I have only considered 5 principal components. Okay, so what is the size of this image? This is a 28 cross 28 image, right? But when I flatten it out, it becomes 1 cross 784, right? And 784 features I have. But what I have done is, out of those 784 features, I have done the principal component analysis, and I have only retained 5 principal components, only 5 features. Fine. So let me give you some demo. I think it'll be more clear with that. Let me start with this. Okay. So this is some code which is similar to what we had done yesterday. A simple code for PCA. Only thing is that I have separated. So this is PCA 2. Below you will see that I have separated EVD and PCA. But anyways, okay. So what am I doing here? I'm doing nothing. I have loaded the MNIST data set over here. I have divided it. I have normalized the data. So the pixel values that the data has is from 0 to 255. So we usually do, for images specifically, we do a division by the maximum value of the pixels. Okay. Then I have flattened it out. So now it has become a 1 cross 784 vector. 1 cross 784. Right? And this is the standard PCA definition that I had defined yesterday. Now what I'm doing is I am applying PCA to MNIST, and I am actually using 50 components. Okay. So I'm doing just normal PCA, and then I am adding back the mean. Whatever mean was there, I would have subtracted the mean somewhere here, right? I had done the zero centering. I'm adding the mean back so that I can visualize the image back. And I will just reshape it because it's a flattened vector now, right? And image is a 28 cross 28 image. So I'll have to reshape it back to the original shape. And then I will just visualize them, okay? So what is happening? So these are the original images. Now what I have done is I have projected this whole data onto some 50 dimensions out of 784 dimensions. Okay. So when you project this data, some of the properties remain the same, right? And that is the whole point of doing PCA, that your properties remain same, your variance is higher, or your variance retention is higher, right? So even though that I am now reducing the dimensionality of this data, now this data is in some less number of features, which is like 50 features. You can see that when you see this visualized image, or when you visualize this image, it's not losing its complete structure, right? You can still identify a 5 from here, a 0 from here, a 4 from here, a 1 from here, and a 9 from here, right? Are you able to see that? These are actually, you can see original data in this. Right? With 50 vectors, we can see that we are able to retain a lot of data, right? Now, let me show you another thing. Okay, let me show you what happens with different number of eigenvectors. Okay, so so actually this is the image that is already generated. I will share this notebook with you so you can play around. Now, let's see what is the impact of choosing, different numbers of eigenvectors or different numbers of principal components. Okay, there's some issue here. Let me see. Extremes not seeing. Okay, nice. Why I have not run this? Okay. So what I've done here is I have taken some images from original MNIST data and I have taken different number of principal components. Okay. So you can see that when I have taken 5 principal components, the image that I'm able to retain is not a very good version of the original image, right? There is a lot of blur in these images. While when I increase the number of components to 20, you can see that, okay, probably not this image. Most of these images are coming very similar to the original image. Similarly, if you increase the number of principal components, your images will be much closer to the original image, right? So what is happening? So whenever we are using more principal components, the variance of the data or the information in the data is retained more. And hence, these image with principal components 100 are much closer to the original images compared to the images that we generated using the 5 principal components. Make sense? Right? So you can see that how we are able to, project back the data once we have reduced the dimensionality of data. Okay. Now, there is something else that you can do with the principal components. You can actually plot the eigenvectors and you can see what information those eigenvectors are retaining, right? So eventually, whatever image that you're generating, right, it will be some linear combination. So it will be like alpha 1 into PCA1 plus alpha 2 into PCA2 plus PC2, alpha 3 into PC3 plus alpha 4 into PC4 plus alpha 5 into PC5, right? It'll be some linear combination. The final image that you're getting is some linear combination because this is a basis vector now, basis vector, right? And the same analogy that if you have a basis vector which is 0, 1, and sorry, this is 1, 0. This is 1, 0, and this is 0, 1. A point here, A and B, is basically A times 1, 0 plus B times 0, 1. Right? The same analogy can be used here that whatever image that I'm generating, the final projection. So now if I project this point onto some alternate basis, right? Suppose I projected here, right? And these are to my alternate basis. These are V2 and V1. So now my new point will be something A dash V1 plus B dash V2. Correct? Yes? No? Harshita? Harshit? Fine. So my the reconstructed images or so these are called reconstructed images. Okay, so there is original image and the one that you are getting after the projection or after dimensional reduction are called reconstructed images. Okay, and there are on much lower dimensions compared to your original image. So these will be nothing but linear combinations of the eigenvectors of your original matrix, which is either X transpose X if you do EVD or X if you do SVD. Correct? So now what you can do is you can actually visualize what these eigenvectors contain. Okay, so in this particular case, when I had just taken 5 principal components, what I've done is I have plotted every eigenvector. Okay, so you can see that these eigenvectors also hold some information, right? So this is like a 0. It looks like a 0. You can see this is like a 3 And this is like, I don't know, again 3. So don't focus there. The focus is that they're capturing some certain part of the digit, right? So maybe this particular principal component is careful of these two curves, right? And suppose PC1, the principal component 1 is careful, or it contains the information regarding these curves. Similarly, the PC5 is containing the information regarding this curve, right? So this will have higher weightage whenever we are creating digits like 2 or say 8, right? But this will not have, this might not have higher weightage when say you are generating an image like 1, because 1 doesn't have this kind of a curve, right? Are you able to understand what I'm saying? That these principal components are capturing different parts of images. They're responsible for different curves that you can see in an image or in a digit. For example, PC5 is basically looking at this particular curve, which is something that you see in a digit 2 and a 8, right? So I can assume that, or I might see it empirically, and I will encourage you to try this out, that whenever you're generating the image for a 2 or an 8, this principal component has a higher weight because this is prominent in 2 and 8. Similarly, suppose this particular principal component is looking about this particular curve, right? Because the other things are lighter. So probably what is happening is for images like 9, 3, these are prominent, right? So whenever I'm drawing or whenever I have an image which is corresponding to 1, you might not see a lot of weight on this particular eigenvector, right? Because that component is not there in images like 1 or say 7, right? So I will encourage you guys, try to generate different images and see how principal components are being added up. Fine. Okay. So the only point I wanted to make here is that there are 2 points I wanted to make here. One is that these different eigenvectors, they contain different information about the images. And the second point is that the reconstructed image or the reconstructed vector will be a linear combination of these eigenvectors. So it'll take information from these eigenvectors and you will club all that information and generate the whole image or whole vector. That's all I wanted to say using this particular notebook. Fine. Okay, so now we understand that this is a reconstructed image. This is much lower dimension. We have reduced the dimensionality. And we are now, and these are the eigenvectors, right? And my reconstructed image is some linear combination of these eigenvectors. Fine. Now, can you observe that these images are not perfect? Obviously, the reconstructed images have some error, or they're not a perfect spitting image of the original image. So there is some loss, right? Whenever there is some information loss, there is some information loss. So there is some information loss whenever we are choosing, eigenvectors or principal components less than n. So n was the total number of features we had. We chose some k principal components, and k is less than n. So whenever we do this, and if k is much less than n, then the loss that we have is much higher. Right? So if this is much less than n, the loss is higher. Okay. So there is a question that I'll take. There will be a minimum data loss using PCA by capturing the most important data compared to feature selection, where we are eliminating the feature itself by capturing most of the variance. That is what the slide is telling about. Okay. So Harshit, I'm not talking about feature selection as of now. All I'm talking about that whenever you do dimensionality reduction, whenever you use PCA, and whenever you choose the principal components less than n. N is the total number of dimensions that you already had in the data. And now you have chosen to represent your data in lesser number of dimensions, and k can be much less, right? For example, here, the total number of features I had was 784. But I chose to represent my images using only 5 principal components, only 5 features, right? So in that case, the loss, what I'm saying is that there will be some associated loss with it, because you will not get a perfect image like this right? Unless there was some redundancy in the data. MNIST doesn't have that redundancy. So what is happening is whenever we are reconstructing with less number of dimensions, we are getting some error. Okay. So that information loss. So what should we do with this information loss? So if you are constructing or if you are formulating, say a loss function, or say if you're formulating a problem, what would you want to do with this information loss? How will you do the optimization on this information loss? Will you maximize it or minimize it? Okay, others? Minimize it, right? So we would want to minimize this reconstruction error, right? So let's see how that formulation happens. Okay. So now let me call this original image to be X and this reconstructed image to be X cap, right? This is what we have been seeing. And this is some alpha times PC1 plus alpha 2 times PC2 plus alpha 3 times PC3 plus alpha 4 times PC4 and alpha 5 times PC5. Okay. Now, yes, the X is one, it's a vector, 1 cross 784. Okay, and it can be 1 cross n. In general, we'll talk about 1 cross n. Fine. So, basically, let me formulate the problem like this. I will say that I am going to project them onto n orthogonal linear orthonormal. This should be orthonormal. So I will project them onto n orthonormal linearly independent vectors, right? Which is v1, v2 up to vn. And we can represent that. So here I am just projecting the data on n principal components, right? In general, I use k, which is less than n. But here what I'm saying is let me project the data onto all the dimensions. Okay. So when I project on all the dimensions, what will happen? So suppose I am choosing k is equals to n. What will be my reconstruction error? 0, right? Because there will be no information loss. I will capture all the variance. Fine. So the only thing that I'm saying with this slide is that you can represent X to be a linear combination of these n linearly independent orthonormal vectors, and xi can be basically represented exactly that, right? But suppose that I chose k, which is less than n. Suppose k is less than n, right? Then I will have some reconstruction error. This is my original vector feature, or this is my original data point, and this is my new data point, which is reconstructed data point. Reconstructed data point. Okay. So now I'll have some reconstruction error associated with this vector. Make sense? Now what will happen? So this is a vector again. Now can I compute the length of this reconstruction? This is just a dot product. So this is a vector. This is a vector. I'm just taking a dot product with itself, right? So this is L2 norm, right? So this is the length of reconstruction. And you already told me that we will minimize this length of this reconstruction error. Okay, so I'm saying this is my reconstruction error. I want to minimize this. The reason that I chose this is because this has a convex form. And you must have seen convex functions while doing linear regression. So this function has a convex form and I can do optimization much better. So I'll not be teaching you the optimization. I'm just going to build the problem for you so that you know that this PCA can be done with this version as well. Okay. So this is a convex problem. This is a quadratic function. So I can optimize this very easily. And you already told me that we will be doing the minimization of this particular reconstruction error. Fine. Okay. So we will minimize this for every sample, right? So total number of samples that we have is M is equals to total data samples, total data points. Right? So we will, for every data point, we will reduce this error, and we want to minimize we want to find a V such that, or we want to find the orthogonal matrix B such that this is minimized. Make sense? And here actually V's K is less than N. Okay. Okay. Now I'll do some maths. If you don't understand that maths, it's also fine. Just know that there is an alternate version of doing the PCA as well. Okay, I'll try to explain this. This is actually very clear, but I'll try to explain this again. Okay, so I'm starting with this. So K is not, so the question is that is K a hyperparameter here? K is still a hyperparameter. So we have already, okay, so what we are doing is, while we are doing this V, right, we will actually find it for N. Okay, I should have not said this. Eventually, we'll choose some K, but here when we find this V, right, we will actually look for N, N cross N matrix only. N cross N matrix, I should have said this. Okay, so this V is N cross N matrix. We are looking for V such that this loss is minimized. Okay, and we'll see how this problem will formulate. Okay. Okay, so you will see a lot of maths on this slide, but it's very simple. So, okay. So, okay, I think I have made one mistake here. So I might have interchangeably used these two things, okay? But this means the new orthogonal vectors only. Orthonormal vectors. Normal basis. Okay, and that's the reason I write it on the slides previously, because I can make up mistakes while writing myself. So I'll just correct this. So if you see like this, you just understand that this is the new projection vector that we have. Okay, so I am now going to expand this particular term that we had in our optimization function, which is this. Okay, so let me start with here. So how many features do we have? So we have originally n features. Okay, there's another thing that I should say before I jump into this. Okay, so the original image. So X is nothing but I is equals to 1 to M. Or let me talk about Xi. So this Xi, the original data point, is nothing but summation 1 is equals to N. I goes from 1 to N, which is the total number of features, alpha I into Vi. Okay, I'm not writing the superscript, but understand that this is a linear combination of these N orthogonal vectors, orthonormal vectors, right? Whereas X cap I is equals to 1 to K alpha I into Vi, right? So here we only have till K we only have till K vectors, right? We are choosing some K already. Suppose K is 5 in the previous example. We'll choose some K. Okay. And so if I do Xi minus X, this, right? What will this be? Look at this formulation. So this is I is equals to 1 to N alpha I into Vi minus sigma I is equals to 1 to K alpha I Vi. Okay. Can you see that these are all the vectors from 1 to N, but these are just the vectors from 1 to K. So what will be the remaining term? There'll be some remaining term, right?
Ma'am, when you choose Xi hat, So will the alphas be similar, or the alphas will also change, no, depending
No,
upon
no, they'll not change. Why will they change?
because they are the new coordinates. Like earlier it was vi.
No. So, okay. So this is the full construction, okay? So I've chosen some V, which is from V1 to Vn, okay? And in this original V, I can represent the whole image in the new basis, which is using n features, n principal components. And
Okay,
this
okay.
I'm representing using only k principal components.
Okay, okay. So X is basically represented in these V's only.
These V's only, yes.
Okay, okay, okay. Yeah,
Okay.
right.
Yeah. So what will be left here? N minus k vectors will be remaining, right? So I will have vectors from I is equals to k plus 1 to n alpha I into pi, right? So this is my reconstruction loss. Make sense? Okay. Now this is what it is. So here what I've done is I have just opened these two terms up. I have j going from 1 to n, features going from 1 to n, and j is equals to 1 to k. And I have subtracted that, and we find out that this j is equals to, now this will go from k plus 1 to n, right? And here the square root term was there, so I've just kept it intact. Fine. Correct? Okay. Now this, right? This is a vector inside this, right? This is a linear combination of some vectors, right? This is a linear combination of some vectors. So this is eventually a vector, and I'm taking a vector square. So what I've done is I have, rather than taking a square, I've just taken like a dot product of this vector. So this is a vector. Make sense? So this is a vector, right? I've just taken the dot product of this vector. Can I do that? Yes, no? We can do that, right? Fine. So now I am going to multiply these two. Okay. So I will just open this up and you have to tell me what kind of terms we'll have. Okay. So this alpha, so I'm keeping the summation outside. I'm just opening this up. Okay. So this is going from k plus 1 to n, and this is also going from k plus 1 to n. Okay. And understand that these are vectors. Right. So what is the dimension of one vector? If I have to talk about this, what is the dimension of this? Where is, oh yeah, this can have errors here, power n. Slight errors on the slides. So at last we have this Vn, alpha in into Vn. Fine. So can you tell me the dimension of this particular vector? What is the dimension of this? So what is alpha I? Alpha I is a scalar or a vector? This is 1 cross 1. This is a scalar, right? It's a linear combination. What is the dimension of this? 1 cross n. So V is 1 cross n, right? So what is the dimension of this whole thing? This is 1 cross n. Correct. Right? So this is, now I'm taking a transpose of that vector. Now this is sum of 1 cross n plus 1 cross n plus 1 cross n vector, right? So this whole thing is 1 cross n whole transpose. Right? This is n cross 1 and this is 1 cross n. So this is actually n cross 1 multiplied with 1 cross n. So the resulting matrix, the resulting thing will be a matrix of dimension n cross n. Make sense? Fine. Okay. So now I have done something here. Now tell me what I have done. So we understand that this is a matrix, right? This whole multiplication will give me sum of matrices, right? Corresponding to every data point, I'll have a matrix. And I can just sum those matrices. But tell me, what have I done here? So what I've done here is, see, this, I am multiplying these, right? So when I multiplied this, so wherever this term is there, which is the same eigenvector is being multiplied with same eigenvector, that'll give me, it's just a dot product. And these vectors I know are orthonormal, right? So i's are orthonormal, right? So what it means when they are orthonormals, so if I and Vj's, let me call that. So whenever I is equals to j, then the dot product of these two vectors will give me 1. And whenever I is not equal to j, then because they're orthonormal, like they're perpendicular to each other, give me 0. Make sense? Right? So hence I will be just left with the scalars. Okay? Make sense? Yes, no? Okay. Now, these alphas, right? What were these alphas? These were my coordinates for projection, right? So it was basically xi transpose bj. We had seen this in the last lecture, that this thing, this is basically alpha now, right? I'm using alphas because they're more easier to handle rather than these caps and superscript and subscript. So what were these? So yesterday when we calculated them, they were nothing but they were dot products between the original data point and the new vector, the new orthonormal vector that we had, right? So I've done nothing. I've just replaced this alpha, which in our earlier slides was x cap ij, right? I've just replaced it with this particular term that we had seen yesterday. Fine? Yeah, Rohan.
Ma'am, so we saw that that this the first line we saw that will be a matrix in earlier slide. So it is
Correct.
one cross n cross one and one cross n. So n cross n matrix and the sum of it. In the second line, when you are writing alpha ij, so I'm trying to relate it to be a matrix, but I'm finding it as a scalar. So how do you justify that it is a matrix in the second line? Ma'am, your video is frozen.
Let me see. Is it better now?
When you are multiplying it,
Yeah.
bj transpose bj would be basically yeah, that wouldn't be 1.
Just a second.
No, but
So
okay,
it's a matrix, okay, and I think there is an identity over here. So this is that. These terms will go to 0 and you'll just add them. So you will do it for all the, so this is 1 meter corresponding to 1 data point.
ma'am, but so vk plus 1, that is a orthonormal vector of
This is
size
an
n.
orthonormal vector. Yeah.
When we are taking the transpose, it is of size n cross 1, and
Yes.
in the right hand side, so vk plus 1, that is of size 1 cross n. So
Correct.
again, when you are multiplying transpose with the normal thing, so you are getting 1 only. So identity matrix is not coming.
I think we need to figure this out. Let me think for 2 minutes, okay?
Okay. Yes, ma'am.
Let me just pause the recording. Okay, so eventually you will be left only with these alphas. Just try it out and we'll see. In some class, we'll take this out session. But as far as I did it, I'm not able to find that particular thing. But this will actually eventually just give you the alphas and not the other values. It will be, the rest things will not be left. Okay, let me just move forward. We'll see this later. Anyways, So here, let's just believe that there are alphas only which are left and rest other things are not there. Okay. So this I can again write in X transpose Bj. Alphas were nothing but X transpose Bj's, which is we have seen somewhere, which we see in the last lecture, that alpha multiplied with the alphas basically are the coordinates giving that or the coefficients of the new basis vectors. Fine. So this is what we have from here. Now let me expand those terms also. Fine. So let me expand these terms also. So this is a square. I'm just so this is how these are alphas, right? So this is a square. I'm just writing it twice, and this is just a dot product. So you can, I think, exchange it. This is just a scalar, right? So you can write it like this also. And then I am taking in, I'm just taking this particular thing inside. This I'm taking inside, this I'm taking outside. So I'm doing summation on all the data points first, and then I will do something about it. Okay. So clear till here. X transpose. So what I've done is I've just written it twice, rearranged it a bit. I have taken the summation inside, and when I've taken the summation inside, then first of all, tell me what is the dimension of every data point, where xi is a data point. What is the dimension of every data point? 1 cross n, right? And what is the dimension of xi transpose? N cross 1, correct? And what are these things? Just a second. These are xi. Okay. This is the data point. This is x1, x2, x3. This is my matrix. These are actually n cross 1. Feature is 1 cross n, no? Data point will be n cross 1, is it?
डेटा पॉइंट तो 1 क्रॉस n होगा ना, मतलब एक डेटा पॉइंट में n फीचर्स है, तो
n
we are
features
writing it
होता
as
है,
a vector.
correct. So this, I don't know what I have done on the slides. So this I have taken from Mitesh Khapra's lecture, which is very public. I have attached the link also in this starting. I'll rewatch it, but I think these things are not clear in that lecture as well. So somehow this has been messed up. Yes, the data point will be xi. It's 1 in n features. So I think I should have written it like this, that it was x transpose x. Maybe. So if I write xi transpose xi, then it will be n cross 1, right? Okay, let me figure this out. I will redo this whole thing. Fine. But what I wanted to really say here was that this eventually, when you do this reconstruction error minimization, right? I'll figure out the derivation for this. But this will actually give you this, which is nothing but x transpose x. We'll come to that. And I think that's what has been messed up. I think I have written them incorrectly. The orders have been changed here, most likely. Fine. So I'll redo this, or I'll share the corrected version of the derivation. But eventually what you will lead here with, you will be having here is the x transpose x, and it will boil down to same thing, that you have to minimize. Similar thing you will minimize Yeah, so not taking care of these calculations. This is 1 plus 1, 1 plus 1. Fine, anyways. Okay, so let me redo this, but eventually what you'll have is that this will come to be X transpose X. X transpose X is nothing but your covariance matrix. Covariance matrix. Right? And you will just replace the covariance matrix over here. And this is your minimization problem. But when we did the other problems, we were doing maximization. Why minimization here? So when I was doing the other things, right, the last two versions, I told you that we are trying to do maximization, something, right? Why there is a minimization term here, or why I'm doing, we have to minimize the loss. But can you see that these are the vectors that we are actually throwing away, right? So here we are minimizing this matrix, right? So what will be the solution? Okay, tell me what will be the solution for this? Suppose there was just one data point or there was just one eigenvector. What will be the solution of this? How will I find the minimum value from this covariance matrix? I will choose the lowest eigenvalue, right? To minimize this whole thing, right? I will choose the lowest eigenvalue. But I was choosing highest eigenvalue when I was doing the other things. When I was finding principal components, I told you to find the highest eigenvalue and keep those. What is happening here is that you are throwing away these vectors, these k plus 1 to n, you don't even consider. Hence, those should correspond to the lowest eigenvalue, right? Where whatever we were retaining were corresponding to the highest eigenvalue. Here we are throwing away the vectors which correspond to the lowest eigenvalue. Fine? Make sense? So this basically boils down to the same thing, that we are throwing away the eigenvectors which have minimum variance. Fine. And the other case was we were keeping those eigenvectors which had the maximum variance or maximum eigenvalue. Fine. So these are just the two different forms of solving the same thing. Okay. Okay. So that is it. I'll correct this derivation. I don't know what happened. Anyways. So I'll correct this derivation and we might to redo, but I don't think the maths is important. Only thing that is important here to understand is that you can have multiple formulations of PCA. There are actually many more formulations of PCA. These are just two formulations. One is by maximization, one is by minimization. Fine. So that's all about PCA. I'm going to talk about applications of PCA now. So one thing that you have seen in the applications is the dimensionality reduction, correct? We saw that we can reduce the dimensionality. We can actually bring down the dimensions of the data to a lower number, and it eventually helps us in comparison, right? So suppose my data is 100K cross 100K image. It can happen, right? If I can reduce it to say 10 cross 10 image, it's a huge compression that I'm doing, right? So I will be able to store these images in much less memory. I can operate on them very fast. My classification algorithms that I'm going to use on these will be much faster compared to if my image was a 100K cross 100K image, right? So it helps us in compression also. The third very important thing is feature importance. What is feature importance? Okay. So let me define feature importance first. I don't know if you guys have seen this before. Feature importance. Yeah, Rohan, what's the doubt?
I'm in compression. So when suppose the whole size is 1 cross 784 or maybe 28 feature. Let's say n features are there, and you chose 5 out of them, 5 features out of them.
Yes.
Yes. So when you're expressing them like alpha 1 into PC1 plus alpha 2 into PC2 like this. So what is the size of this new vector that is also 1 cross 784?
That will be, okay, that's a good question. So what will you do is you will only store those eigenvectors. Yeah, I should have elaborated on that. So you will store those PC1, PC2, PC3, and PC4 and PC5. Okay. You will store these 5 eigenvectors and only you will store these coefficients. And that's where comparison is coming from.
Okay. So the pixel size is again same, 1 cross 784.
You can get the same size of image, and hence you were getting the same size of image here as well.
Right. In the reconstructed image.
Yes. But what will you store is you will only store these PCs, these features, and you will store the coefficients of them.
Okay, ma'am. Yeah.
So it will be like L1, alpha 2, alpha 3, alpha 4. So this is like huge compression that you're doing. And this is used in images to do the compression. Okay. Fine. Good question. Feature importance. Okay. So let me talk about feature importance. So I have, say, these features, right? Suppose X1. Yeah, Harshit, what is your doubt? X1 and X2.
Like in PCA, like in PC1, PC2, like we are considering all the features, but we are not using the full data. That is what it means, right?
So earlier, suppose your data point
we are
was
not reducing the features, but we are reducing their variance. No, like we are removing lowest variance thing, right?
So we are removing the dimensions which have the lowest variance, okay?
But not the features completely.
Okay, so first of all, the features, right? Whatever you have are actually linear combinations. So new PC components, right? So PC1 will actually be a linear combination of the original dimensions, so original features. So you're not completely throwing away any feature. Right? So for example, this will be alpha 1 x1 plus alpha 2 x2, something, alpha n xn. Okay, so PC1 is a linear combination of all these features that you already had in the previous. Now it's some linear combination. So you're not throwing away any feature up front that, okay, I'm not going to use this feature.
And that 5 number is of like we are choosing top 5 PCs.
Correct.
With most variance. Yeah. Got it.
Yeah, so this will be like some beta 1 x1 plus beta 2 x2, right? Beta n xn. Yeah, so we're not completely throwing away any feature.
Got it.
Okay. So we have these features, right? Now, feature importance basically tells me how much a feature is important in, suppose finding these principal components. So I was coming to this thing what Harshit asked. So every PC, right? Every principal component is actually a linear combination. Of original original features. Can I say this statement that my PCs, my principal components or my eigenvectors are actually linear combination of the original features? I can give you an intuition for that. Suppose these were my original dimensions or original features. Right? Now you took some eigenvector here. Right? So this eigenvector is a linear combination of these two dimensions. Now suppose this is 2, 2. This eigenvector says 2, 2 vector. This is 2 times 1, 0 plus 2 times 1, 0. This is some linear combination. Yes. So whatever your principal components are, right? They are actually the linear combinations of original features, right? Now here in this case, this particular dimension and this particular dimension are contributed equally to this particular vector, right? Now suppose my eigenvector or my principal component was like this. Okay. and say this vector was, I'm just taking an example, so this might not be orthonormal, but suppose this vector is 3, 1. I'm just assuming, right? So now this vector, this new principal component, which is 3, 1, is 3 times 1, 0 plus 2, 1 times 0, 1, right? So this particular original feature, which was this, attempted correctly, 0, 1. So this feature is now contributing 3 times more than this feature to my new dimension. Make sense? Others? Make sense? What I'm saying? What I'm saying is, let me redo this again here in a better way. So this is my first dimension. This is my original features, right? Now, in this, suppose this was my principal component, which is PC1. Okay, some PC1 is there. And say this is 1, 1. Right? So what is 1, 1? So 1, 1 is nothing but 1 times 1, 0 plus 1 times 0, 1. Right? So both of my features are contributing equally to this new principal component, right? So these are equal contributors. So they're equally important. Now, suppose I had a principal component. So this is my PC1. Now, suppose I had a principal component, which was like 3, 1, right? So this is nothing but 3 times 1, 0 plus 1 times 0, 1, right? Now, my first feature, which was, say, F1, and this is F2. Now, my feature 1 is more important than feature 2 because feature 1 is contributing more to my PC2. Make sense? So this information combined with the explained variance ratio in the last class that we had seen gives us an idea about how important are our features for separating the data or, to recognize this data distinctly. Fine. So each principal component is a linear combination of the original features. The coefficients of these linear combinations indicate the contribution of each feature to the principal component. And features with larger coefficients have greater impact on the principal component, right? So this is feature importance. Along with this explained variance ratio, we can actually give a number to feature importance. So explained variance will give you a very good idea about what is the feature importance. Okay. So I had a piece of code that I did not run yesterday. So this is that piece of code. So here, right? I don't know whether this will run. Status maintain, it will run, otherwise I'll have to run the whole notebook. Right. So top feature contribution. Okay, so what I have done is I have taken the eigenvectors. So the coefficients inside the eigenvector or the values in the eigenvector will give you basically the idea how much important every original feature was to this new eigenvector or the principal component. Okay. So for example, in the example that we saw yesterday, right, for the iris data set, there were 4 original features and we then reduced it to 2, right? So there are 2 principal components that we have. So you can see that for the first principal component, this petal length contributed like 0.85, right? And if I print the eigenvectors, you can see this eigenvector being printed. So this is the first eigenvector. You can see that the third column, which is x dot columns, which is data dot column, this petal length basically had the value in the eigenvector is negative 0.85. So the feature contribution is basically 0.85. Then sepal length has a feature contribution of 0.36 and similarly petal width and sepal, right? Sepal width. So what is the most important feature or what is the feature which is contributing the most to this PC? One is petal length, then sepal length, and petal width and then sepal width. Similarly, for PC2, sepal width is contributing more, sepal length is contributing lesser than that, and petal length and width are contributing least. Right? So we can compute the feature importance, and how you determine the feature importances. So these are, so you just multiply, you'll take the absolute value. So eigenvectors can have a negative coefficient also, right? So they can have negative values, but we take the positive, we take the absolute values of that. We multiplied with the explained variance ratio that we had seen yesterday. And that gives us the feature importance. I can plot the feature importance. So for the first principal component, you can see that, so this is the first principal component. This is corresponding to the first principal component, okay? So the feature importance, you can see the highest feature importance is coming with petal length. Sorry, this should come with what have I done? 0.33, sepal width is 0.12. 0.74. So this actually basically is important. Okay, I'm missing some information here. Okay, just look at this particular, this I will come to this later. So this I have plotted the contribution or the feature importance for the first principal component using the explained variance ratio and the feature contribution. So you can see that the petal length, as you can see, petal length here was contributing the most to this, right? So I've just plotted that value over here from the feature importance. Okay, so petal length is the most important feature for PC component 1, PC principal component 1. Then the second one, and these two are almost contributing equally, and sepal width is the least contributing factor or least contributing feature to this particular principal component, right? And hence you can generate a feature importance for these. Just multiply with this. And I have feature importance as this. First principal component is retaining 0.92 times. Okay, so what is happening is that these values. So first principal component, as we know, it was retaining 92% of the variance, right? We had seen yesterday. So so this value of explained variance ratio is getting multiplied with every coefficient of the eigenvalue, and that gives you the feature importance. Fine. So PCA is also important in determining what features are important for your data. For example, on this basis, you can say that petal length is a very important feature. We can do it for the second eigenvector also. I'll have to rerun this notebook. I have not run this, so it's giving me an error. But basically, the point of whole of this exercise is to say that you can actually determine importance of every feature, and hence PCA is helpful in doing feature importance. And on basis of this, right, on basis of this plot, let me run this again. So basis on this, what Harshit was saying, that suppose that you find that a particular feature is not important throughout, right? It's not contributing much to any principal component. You can just remove them even before you start doing any classification algorithm. You can just completely throw them off. Fine. So I think that was your doubt, Harshit, that are we throwing away vectors or are we throwing away features? You can actually throw them away if you find that your feature importance is like least, right? And before you proceed to a classification algorithm or a regression algorithm, you can just throw away that feature and keep all these features which are important intact if you don't want to reduce your dimensionality. Fine. Something I have done here which is not neat. Now this is the feature. This was the second principal component actually. Second principal component. So you can see that this sepal length and sepal width are contributing a lot for the second principal component, like we had seen over here, right? And you multiplied with the importance of that particular principal component. What is the importance of the principal component is the variance that it is capturing. That will give you the complete feature importance. Right? So it's a very important algorithm to do feature importance, and based on this you can do feature selection, which Harshit was talking about. Feature selection is nothing but you are selecting only the important features and you are throwing away the rest of the features which are not important to you. Okay. Any doubts? Here, we'll solve some questions on PCA now. So if any doubts, please ask. Otherwise, we'll just proceed. Okay, let me start with the questions today. Okay, so this is an MCQ. It's saying that if first principal component explains 60% of the variance and second explains 30% of the variance, what is the maximum possible variance explained by the third component in a three-dimensional data set? Okay, everybody answered it correctly. So we know that it's a three-dimensional data set. So the total variation explanation will be 100. So if somebody is contributing 60 plus 30 plus x, that should add up, that should add up to 100. So it's a very simple question. So x is equals to 100 minus 90, which is 10, right? So A is the answer. Fine. Okay, these are just for your understanding. We'll make them just for your understanding, just to understand that you have understood these questions. Okay. So which of the following is not a valid reason to use SVD instead of eigenvalue decomposition for PCA? So the option is better numerical stability, ability to handle non-square matrices directly, more efficient for data sets with more features and samples, and guaranteed orthogonality of principal components. Which of the following is not a valid reason for doing SVD or choosing SVD over EVD? Okay, Harshit.
Sorry, ma'am, I didn't cover SVD on those things.
Yesterday we talked about this, no? You were there in the class, no? Yesterday?
Yes.
This was
No,
discussed
I
directly in
couldn't.
class. Okay, fine. So the answer is D. Okay. Whether you do EVD or SVD, you will always get orthogonal principal components, right? So it's not even a choice. Like it's guaranteed that you will have. So this is not a differentiating factor. Not a differentiating factor. Differentiating factor. And rest of all the points we discussed yesterday. So I told you that has a better numerical stability because the eigenvalues don't get squared up in SVD. So the errors, the rounding of errors are less in SVD because you're not squaring up the matrices or the eigenvalues. And then your ability to handle non-square matrices directly, which is definitely a point which we prefer in SVD. Then more efficient for data sets with more features and samples. So this also we discussed yesterday that it is more efficient for data sets which have more features than the given samples. Okay. Okay. Now, so the option is D. Now, if the data set has a perfect multicollinearity between two variables, means that they are perfectly correlated. Correlated like, so perfect multicollinearity means suppose there are two features X and Y. X is say 2 into Y. So this is multicollinearity that they are exactly related to each other. How do you think will affect the PCA results? Others think about it. What can happen? Okay, Harshit. Okay. So the answer is one eigenvalue will be exactly 0. Okay. Because the variance for that particular feature will be like 0, right? Because it is already being captured by other feature, right? So the eigenvalue will come 0 corresponding to that. And rest others will see why they're not true. So if say all the eigenvalues are equal, what it suggests is that oh, sorry. So all the eigenvalues are 0. What it means is that, sorry, all eigenvalues are equal. It will suggest that all the eigenvalues or all the directions have equal variance, which is not true in the multicollinearity, right? Here it's saying that two things are capturing the same thing, right? If I would have said that they are, so you should think about when the variance will be or when the eigenvalues are equal. So when they are capturing equal variance, for example, I don't know if I can create a data set like that. Say a perfect circle kind of a thing you have, right? A circle of say radius 1, right? Then in both directions, your variance is equal, right? Make sense? And hence the eigenvalues will be equal in that case, right? So whenever your variance towards both the sides is completely equal, then only your eigenvalues will be equal. In this case, it will not be equal. The second part says that the first principal component will explain 100% of the variance, which is not true, right? So 100% of the variance will only be explained, or you will have 100% of the variance only when you have data, or you have all the data in only one direction, right? There is no variance here. right? So there is just variance on this particular dimension. You're representing data in 2 dimensions. Then only your first principal component will have 100% of the variance. And PCA will fail to converge. This is also not true. PCA will converge. Okay. PCA will give you the eigenvalues. You can always diagonalize X transpose X, right? So there is no convergence as such. It's just that one of your eigenvalues will be 0. Fine. I should put this here so that we are more clear that this is related to this. Okay. Fine. Clear, everyone? Okay. This should be easy. In a data set with 1000 samples and 10 features, what is the maximum number of non-zero eigenvalues in PCA? So maximum number of non-zero eigenvalues. So eigenvalues basically tell you the variance of every feature, right? So if every feature is explaining some variance, then we'll have non-zero eigenvalues. Okay. Varshita? Okay. Did you understand the last question, Varshita? Because that's important, okay? They can ask you these kind of questions. If I was making gate paper, I would ask a question like this. Okay. So let me give you a hint. Okay. So variance of feature is directly related to variance of feature is directly related to the eigenvalue, right? So they're asking what is the maximum number of non-zero eigenvalues. So we saw that maximum number of non-zero eigenvalues will be when, or the eigenvalue will be 0 when one of the feature is highly correlated or multicollinearity is there between 2 variables and one of the eigenvalue will be 0, right? Suppose all of my features does have some variance or they are not correlated to each other. Okay, so fine, everybody's on the same page. Because the maximum number of features that we have is 10, then we can have this here, right? So the maximum number of eigenvalues which are non-zero, you will always get to be this. Fine. Okay, so there is a modification that Rohan is suggesting we can do. So let me just take a copy of this. So I'm doing a little modification here. I'm also adding a constraint that there are 2 features such that this is there. Then what is the maximum number of and I'm just removing those options. This is an NAT now. Okay, why 1000, Harshit? So see, what is happening is that these features are correlated, highly correlated, or there is a multicollinearity between these. So the eigenvalue corresponding to this and this will be 0. Right? Because from the last question that we saw, that whenever the features are like related, like here this was linearly related, here also there are linearly related. So the eigenvalue corresponding to these 2 features or any of these 2 features, any of 2 of these 3 features will be 0. Hence, you will have maximum number 10 minus 2, which is 8. Okay, so 2 of these features will have eigenvalue 0, and then we'll have 8 principal components with non-zero eigenvalues. Fine. Okay. Suppose that you perform, so the next question is, suppose you perform PCA on a data set. Okay. And you find that the first principal component is this. So your first eigenvector is 0.71, 0.71. What can you conclude from this? That two original variables are perfectly correlated. Two original variables contribute equally to the first principal component. The first principal component explains 71% of the variance, or the original data was two-dimensional. So this is a MSQ, okay? This is not MCQ. This is MSQ. There are two options which are correct here. Okay, so everybody got this is correct. That two original variables are contributing equal to the first component. Only confusion is between C and D. And this is incorrect, right? Because we know if they are perfectly correlated, then one of the eigenvalue will be 0, right? So this is not true that they will be perfectly correlated. These two we have to think about, right? So the first principal component explains 70% or 71% of the variance. This is not true, no? Because the coefficients of my principal component don't tell me anything about the variance that they're capturing. The variance that they're capturing actually comes from the eigenvalue. Correct? So the variance is something like lambda I summation lambda i's, right? So explain variance is this, right? So the first problem, so this is not true. This is true, that the original data was two-dimensional because the PC is in 2D, right? Fine. So this is fine. This is actually true. So B and D are the answers. This is an MSQ. Fine. I think this is the last question. Yeah, Harshit, the doubt.
In this question, like we have here two principal components. So by using just principal components, we can tell that it is a two-dimensional data, because we can take based on the k value. We can take
No. So this is the principal component. This is the eigenvector. These are not. So we have, this is the first principal component, and this is the value of that principal component. So PC1 is equals to 0.71, 0.71. We have said nothing about number of principal components here.
Okay, got it.
Okay, makes sense? Fine. Okay, so this is the last question. So in PCA, if we have negative eigenvalues, we can still take the eigenvector corresponding to that eigenvalue and think about what will you do with that eigenvalue? Like how will you explain the variance? So if your answer is true, you should tell me how will you take the value. Okay. How will you explain the variance, or how will you take that value? Okay. Ashta? Okay. So this is not possible. Okay. So PCA will never have negative eigenvalues. I can do PCA with singular values also, no? Correct? Yes, no. Are singular values negative? Okay. Should think about the question. Are singular values negative? They are never negative, right? So this is the question I made. Okay, so they are never negative, right? So don't do these kind of things in GATE exam. I'll be very disappointed. Fine. So PCA will always have positive or zero eigenvalues. So what kind of a matrix is this? X transpose X. symmetric. So if it has positive or zero eigenvalues, what do we call that kind of a symmetric matrix? Positive, semi-definite. Semi-definite. Right? So this is not possible. PCA, we will always have something that you should work on. Okay, so something that you should figure out. And also you can see, right, X transpose X. This is coming out to be the covariance matrix, right? And you have square terms on the diagonal and rest everything you are saying is zero after the projection, right? But okay, you can argue that this is the original one, but think about it. I can do the principal component. The best argument I can make here is that I can do it with singular values also. And singular values are, and I have told you that the singular values are square root of eigenvalues. So, or singular values are never negative. Hence, we will always have positive or zero eigenvalues. Or zero eigenvalues. Fine. If this question comes in exam, please don't make a mistake. Okay. So this was the last question that I wanted to cover today. And this is also the last lecture for PCA. I have attached the link for the lecture that I have referred for this particular lecture, the reconstruction lecture. So it's a lecture by Professor Mitesh Khapra in IIT Madras. Obviously, I need to still figure out the derivations. I assume that the derivation will be okay, but it doesn't look like it. So I'll redo the derivation and I'll probably edit this video out. So this is what we have learned today. So we have learned more about the SVD, right? We established why SVD and EVD will give me the same thing, the same vector, the same orthogonal V, right? Then we did PCA via reconstruction error, which is the third version of the PCA that we have seen. And I heard in some lecture of Mitesh Khapra that there are 10 variations or 10 way you can do PCA. Okay, and he makes a very funny comment around it. So probably you should refer his deep learning videos as well and see what he has to say about the PCA. Then we looked at some of the applications of PCA and we did some questions on the PCA. And we also saw, there was another thing that we saw was that the reconstructed vectors, are lossy images or lossy vectors, right? So this is also we understood. They are linear combination of PC components, linear combination of PC components or principal components, PCs. So these are few takeaways that we have from this lecture. And with this, your PCA ends. And I will see you in the next lecture. Okay.